Okay. So tomorrow will be quiz, right? No, not today. Not today. We change to tomorrow. Okay. So tomorrow will be quiz. But I would like to just a little bit review chapter 11. What is the whole concept and which points that you need to emphasize? Okay. Before we continue. So I think around 20 to 25 minutes we can have some review, or maybe just 15 minutes, just a quick review. Okay. So let me put here chapter 11 review. And next week we have midterm, right? Okay, the midterm. So it should be November 3rd, right? Okay. So this will be for quiz preparation. Quiz preparation. Tomorrow. Okay. So chapter 11, we mostly deal with the series. So we first deal with the sequence, which we usually deal with the limit, right? And then we deal with the series. And then for tomorrow's quiz, we are going to more in line with the series, which includes first is determine convergence and divergence, which we emphasize through several methods. The first method we learn is we call the divergence test. And I think it's the very simple method, very easy to use. You just check the limit. When the limit of the an is not equal 0, or it does not exist, then we can conclude the series is divergent. So we take the limit of the an. Okay. We want to make this not equal to 0, or doesn't exist. Then the conclusion is divergent. Okay. But if the limit is 0, then we need to have another method. We have integral test. As long as the function is positive and decreasing along the way, the function means the series. Okay. Then we can take the integral. Okay, you can take the integral test from 0 to infinity. Okay. Let me just write fx dx. Okay, just fx is this series. And this method is basically taking some part of the integral, and we call this the improper integral. So whenever you see some function that decreasing and positive, and my tips for the integral test is the function can be integrated using some substitution method or integration by parts. Okay, if you see those functions, then you can directly use the integral test. But if you feel trouble with the integral test, and if you feel another way is more comfortable, you can just choose another way. Okay? Another way is either comparison. We can have two methods, direct and limit comparison. Direct method is comparing with another function or series. Compare with another. Let me write with different color. So this is compare with another known series. Let's say this is Bn. Okay. So if An is less Bn and Bn converge, then An converge. If Bn diverge, no conclusion for this one. But if the Bn is less than A, and if Bn diverge, for sure An diverge as well. And limit comparison is more applicable. Okay. So if you cannot directly compare two series, if the series maybe you cannot prove that it's less or greater than the other one, then I suggest to use the limit comparison test, which taking the limit of the An over Bn, and it needs to be equal to some L. And B is the known series. So if this series Bn is diverge, then An also diverge. If Bn converge, they're the same. An also converge. Okay. And usually this direct comparison test, you can think the known series from the P series, okay? The P series or geometric series. Okay? For example, this one here, the known series Bn, maybe the known series like 1 over x with power of p, or maybe n. Okay, sorry, maybe n with power of p, or geometric. AR with power of n minus 1, or what else that can be. I think mostly the cases will comparing either the 1 over n with power of p or a geometric series. Okay. Or sometimes you need to process inside the direct or indirect comparison test. For example, you know some series, but you need to use this known series and prove first whether it's converged or diverged with another method. And after you get converged or diverged, you can take back to the statement. Make sure either this case or this case, okay, and then make sure all confirm. Okay, all confirm. Like for example, in this part here, this A, if A is less equal B, and B is converged, A is converged. But if B diverges, then there is no conclusion, there is no guarantee, or there is no confirmation whether A will also diverge, because it's not. If you think clearly, like if this one already less, this A is already less than B, and B is converged, A is impossible to be diverged, right? It must be also converged. But if this part here, if A is smaller, right? A is smaller than B. If A already diverged, B cannot be converged, right? Okay, cannot be converged. So this B, if B diverged, then A must be diverged. Okay. Okay. So as long as we confirm with this statement, then we can get the solution. Or if we cannot really directly compare it, I suggest to take this into our limit comparison. Okay. The idea for limit comparison is we are going to cancel each one of them. Okay. So we are going to take the AN and BN, and then we try our best to cancel and then take the limit, and then our expectation is it will have some number or some value, which later we can confirm whether if B is diverged, then A also diverged. If A or if B is converged, then A also converged. Okay. Now the other method like alternating series, alternating series is easy to be found. Okay, whenever you see any negative 1 with power n minus 1, something like that in the series, this indicating alternate series. So if we take the n like this, suppose that this is our series like that, we are going to focus on the A. Okay. For alternating series, at least 2 points, okay, we need to make sure that it is decreasing, okay, that AN plus 1 is less equal AN, or just less AN, and second, the limit of the AN is equal to 0. As long as you can prove this, then you find converge. But then, in this alternate series, there are several conditions. Okay? We can have absolute convergence. We can have conditional. And we have diverge. Right? At least these three conditions. Okay, I hope you still remember how to make sure whether it's absolute and conditional. I think absolute is if you put AN or if you put into the alternate series, both are converged, okay, for absolute. For conditional, maybe if you look just AN, maybe it will be diverged. But when you see the alternative form, maybe it converges. We say it's conditional convergence, okay? But if the other one is all divergent, then it's divergent. Okay. The other one, what else we have? The ratio and root. Basically, this is taking either the ratio is taking this, okay, and this should be less equal, or let me write this is some L. Okay. And for the root one, we take the square root of n, and then taking the same thing like that, and it will also need to have equal into L. And L need to be greater than 1, right? So we have a convergent for convergences. I think mostly that is the method that we usually check, right? Yeah, I think, yes.
The ratio said the root test is only an plus 1 over an.
Oh yeah. Why I'm writing like the ratio. Let me just write an, okay? I think this should be okay. And the an usually having the power of. Yeah, comparison, geo, okay. Convergence, divergence. Okay, and then after the methods, another type of the question will be about the power series. Power series, it will relate to the radius of convergence and the interval of convergence. And the power series we can later represent as a function. We can remember this x to the power of n, which this is 1 over 1 minus x. This is one example on how we represent the power series. And the more general, the power series is the sum of the Cn x minus a with power of n from n, let's say, equals 0 to infinity. This is the general forms. Okay, so since we have, so before we state that we only take some x, okay, in which the x is having the exact number, but now we have some sort of like a distance, okay? So it's not really just one x, but we are going to see some interval, or even between the interval we see the radius. So the convergences is not a single point, but it can be some interval. So through some process within the power series, if we can prove some series, or maybe we can see whether it has some radius, or perhaps it's just a single point, or maybe we can have for all x. That's the possibility. Okay, so the way we check is basically taking the ratio test. Okay. So check. So this will relate to ratio test. So the ratio test become important. So ratio test and then testing whether the it has radius for all x, or a single point convergence, or radius is basically this x minus a, the distance, or even maybe radius become a, or maybe it could be a plus r or a minus r. Okay. And interval will be around this a plus r and a minus r, a plus r. But we need to check. Okay, we need to check. Let me write here. Don't forget to check the endpoint. Okay, so what's the deal with this? Okay, so you check the ratio test. You get some conclusions whether we can include all x or it is a single point, so there is no radius. And then if we can have some interval of convergences, then this is still not a complete solution. If we want to complete the solutions, then we need to check this all the endpoints, check again to the original equation. If one of them are convergent or both of them convergent, then we need to include. So it can be includes. Okay, so it could be maybe not including anything. That's one possibility, or including the right endpoint, or maybe the left endpoint, or maybe both. Okay, so it could be four possibilities. So check the endpoints, and then so there's the power series basically looking for the radius and the interval of convergence, and then we can represent the series as a function from this structure. So whenever we can find any function that can be represented as power series, we need to see the structure. If we can somehow write something like this or factor out some components from the functions, and then we can see the structure, we can use this method. So basically, we can exchange all the components, okay, to this power series action power of n. Okay, I think we have some examples, but the more interesting part is after this representation. Okay, so we can generally use Taylor and Maclaurin series to represent power series as a function. So that will be more general. So we can have a more general rule is using Taylor and Maclaurin. Okay. So the functions become for the Taylor f derivative power n. It means how many we derive, divided by n factorial, and then x minus a to the power of n. This is Taylor. Okay, Taylor. The Maclaurin, the same, but a is equal to 0. Okay. So f of x this is going to be fn, and we put 0, and then n factorial, and then x with power of n, and this will be the Maclaurin. There are several functions that I suggest you to at least know how to get it. Okay. Like the 1 over 1 minus x, for sure this is the standard one, e to the x, and then sine x, and of course from sine you get cosine, and then tangent inverse x, and then ln 1 plus x. For the tangent inverse, also ln, you can think this too. If you are maybe feeling, if you try Taylor-Maclaurin is too long to produce, you can think this too from the 1 over 1 minus x. You can think we can derive or integrate, okay? And then using the idea that this is actually power series of x to the power of n. And then we can exchange. And then we know that the tangent inverse, if we derive this, it will be 1 over 1 plus x squared, which is, we can write this as 1 over 1 minus x squared. Okay? So we can think also from here that this is going to be 1 over 1 plus x squared. So this will be 1 minus x squared. And then from here we can write this one, and then exchanging x with negative x squared. So negative x squared will be put inside the x with power of n. So we get the power series, and then to get into the tangent inverse, we need to integrate this. Okay. That is one way. Or another way is we take the Maclaurin series one by one. First derivative, second derivative, and then the third derivative, and then put the value, and then put back inside here, and then we can have some sort of expansion, and then we can have some patterns. Okay? That's another way. And ln is the same. Ln, if we derive this, it will be 1 over 1 plus x, which we can change with negative. Okay? So we can have that, and we know that this can be 1 minus x. Okay. So just a notion that I think if you just focus on knowing this as the x to the power of n, and you know the e to the x, this one become 1, right? Because e to the power of 0, 1, and for all the series or the terms is also the same 1. Right? So it will be x to the power of n divided by n factorial for e. It's not too complicated, right? For e. For sine, I think you need to do some Maclaurin, because sine for some parts there will be 0, because if we plug in x equals 0, it will be some part of sine will be 0, right? Because if we derive, if we cosine, negative sine, and then negative cosine, and then you can have some terms. Maybe 4 terms is enough. You will see that whenever we have the sine, it will be 0. So it will have the odd number in it. And if you would like to know the cosine for the series, for the Maclaurin, then you could derive from sine. So derive the power series. Okay. So I think that is the one that I would like to emphasize. So if you get some summation, you have the pattern, you could relate it to one of this, and then try to manipulate the structure and find how it can be the power series. Okay. So that is for sure one of the questions about that. Okay. So please check again one of the questions. So for example, if you get like maybe something plus something plus. So first, to imagine how it looks, and you could relate to one of this function. Okay? If this is having some e, maybe it will be related to this e. Okay, maybe. Or even if this is going to be some number, you need to see like what kind of number and then what kind of function it has for every term. Can we relate to some of this or not? For sure, there will be one question about that. Okay, and one question about radius or interval of convergence for sure. Okay, that's a little bit review. So hopefully you can check. I think I put some. Have I put the last year midterm in the Moodle, right? Or no? I did, right? In the Moodle?
Yes.
Yeah, you can check that out. Check especially the chapter 11 questions. Right? And also to prepare for next week midterm, right? Okay, you can check that out. Later I will, if I have time, I will prepare some video, but if not, I will just let you know the answer key. Okay. Now I think we can move a little bit, chapter 14 again, okay, for a while. Okay. So last discussion is up until this higher derivatives, okay. So we are going back to what we call as a tangent plane. So recall that in calculus 1 we have tangent lines, right? We have tangent line. So you have a function like in 2D Cartesian, and you have this, right? So for example, in P here, you have a tangent line like that. But now, in our calculus 2, we are going to have a tangent plane. So what does this mean? It means that we are going to have a surface like this picture here. So we have a surface S, and then if we look at the x-axis and y-axis, I think on the previous part we know that when we put in this point, and then this point can relate on this xy plane, you can see that this line, the red line, is actually reflecting the y-axis and x-axis. Okay. So this T1 is reflecting to the x, and the T2 is reflecting to the y. If you remember, in the calculus 1, this green line, the slope is actually the first derivative, right? But now we have a function of two variables. This T1 and T2 is actually the same or similar reasons with the first calculus, which means that this T1 and the T2 is actually our derivative. But this will relate to our partial. Since this is on x, this is partial with respect to x. The T2 is partial with respect to y. Okay? And then these two lines, if we draw like with it perfectly, it will make a plane. Okay? So you can imagine that in the surface, like for example, in the surface here, like imagine you put some cover or you put some like a books, okay? And then this is what we call the tangent planes. Okay? So when in two variables, function of x and y, we are going to have a plane, okay? So let me write the original equations that any plane passing through P, let's say P is having some coordinates x, y, z, like that. It has equation. Remember, in three-dimensional forms, we can have A x minus x0 plus B y minus y0 plus C z minus z0. Okay, this is for any plane. And then let A equal negative A over C and B is negative B over C. So we need to rewrite this. So we divide all the terms, divide by C, okay. And then we are going to write Z minus Z0, and then I will move A and B to the right side, so it's still positive because I will let A equal the negative, right? So this will be equal to A x minus x0 plus B y minus y0, okay? And because we know that T1 is actually, so T1 is actually our partial x at some point, and T2 is our partial y at x0, y0 at some point. Then we can imagine that this A and B is actually our partial. Okay. So this means that A is actually our partial x, and B is partial y. Okay. So if we want to look on the equation of tangent plane, to the surface z equal f x y, two variables, at this point P, this means that the z minus z0, okay, according to our plane equation, is equal the partial x at this point, and then multiply with the x minus x0, plus the partial y at this point, multiply the y minus y0. Okay. See, it's actually pretty similar to in calculus 1. So if you remember in calculus 1, we deal with the line equations. Okay. In calculus 1, we deal with line equations. So we deal with somehow this is x0, y0. So we deal with y minus y0 equal m x minus x0, and we know the m is actually, if this is f, then m is f prime, or in this case at x0. Okay. But now, since it is having a plane, then we are going to have this structure here. So partial x and partial y. Or if you would like to confirm all the T2 and T1, you could see that we can make some rectangular or a triangle from the T1 and T2 if we somehow so we can write the T1 is actually, so T1 or T1 equal A equals z minus z0 divided by x minus x0, and b is z minus z0 divided by y minus y0. It means for t1 is z divided by x. Okay. Imagine like a triangle, it has an angle theta, the tangent theta is this divided by that. Right? Okay. And the same way with the t2, we have here a triangle. So we define the z divided by this is y. Okay, can you see the triangle? So it means here. Let me take the yellow color. And then this will be another one. Okay. So we can have this also. And that's why we're sure that the A, B, and this is basically also related to the definition in partials. We can say that the difference in z divided by difference in x, or we say this is dou z, this is dou x, this is dou z, this is dou y. Okay. We can also think visually. Okay, so perhaps at the very beginning, this is somehow looks like complications, right? But if you think clearly, like you pick some point, okay, and then if you could imagine that you could rotate and see what it looks like if we see that this T1 and T2, if we reflect to this xy, is actually on x. So T1 is on x, right? On x like that. It has this line. And T2 is this line, which is on this y. This the parallel with y, right? Okay. So for now, we have this structure for the tangent plane. Okay. Later, for several sections later, we are going to have a more general rule how to get the equation of tangent plane directly. So this is one way to see. So we have a function of xy that is our surface, and then from that function we can have partial x and partial y, which we can put into here. Okay. And then the rest is just taking the value of each one of the z, x, and y. Okay, okay, I think that's it. Okay. Just adding this and finish, okay, for today's class. So don't forget tomorrow, quiz. Okay. All the emphasis that I point out before, don't forget that. At least about Maclaurin, the power series about radius and interval, and finding the convergence or divergence, testing the series. That's also. No. For quiz. Yeah.
Not that part.
Yeah, no. We already have quiz for that part.
Okay.
Yeah, so not including the parametric. But parametric will also include in the midterm, okay? In the midterm. The midterm will include, but for tomorrow it's just only series, okay? Series, sequence and series. Okay, I hope you study well. And if you have any questions or any difficulty, you can email me, okay? Find some questions, maybe it's difficult for you to answer, let me know. Okay? Sometimes students ask me, and then through email, I will, as soon as possible, I would like to reply, but sometimes I need time. Maybe if you email me in the morning, maybe I will reply you. If I don't have anything, I can reply you directly, or afternoon. We have something to do maybe at night. Okay.